Good evening. My name is Cesar Diaz, and now in this presentation I will go about my Project 2 external challenge for the class of my 1321 Statics. The objectives of the project are to design and build a lander made of spaghetti able to protect an egg from the impact of 1 meter drop. Use the structural analysis methods learned in statics class to ensure the success of the design and apply the concepts of statics and dynamics to determine the forces and impact energy transmitted to the lander. The design requirements for the lander are a minimum drop height of 1 meter, a maximum weight of 450 grams, a maximum landing pad size of 30 centimeters times 30 centimeters, which is the same as 300 millimeters times 300 millimeters, and that glue can only be placed at the joints, not along the members of the design. Brainstorming. So the design of many Mars and Moon landers were reviewed before choosing a final design. Many useful ideas were taken from these devices to ensure the success of the design, including the shape of the legs and where to assemble everything. And also, three preliminary sketches were drawn before choosing a final design. Okay, so from the three like real Moon and Mars landers reviewed, the first one is the NASA InSight, which is the first mission to explore Mars' deep interior, which landed in November 26, 2018, and it's basically this is not a rover; it's just like a lander. And it's basically investigating the composition of the soil of Mars, looking for processes that shaped the rocky planets of the solar system more than 4 billion years ago. And so the structural design for this landing is like landing device is composed of three main legs, uh, like here, here, and it's composed also. Each leg has like two supportive shock absorbers, and you can see that like the leg is placed a little above than the shock absorbers, and this has some implications that we will see in a moment. The Apollo 11 landing model, which is basically the landing model for the first for the Apollo 11 mission, which as we already know, which carried the first human to the moon in 1969, and for the structural design is composed of one leg here, which is kind of like supported by this member, and also by these choke absorbers here. However, after reviewing this design, it's composed also from four legs. And after reviewing this design, it was thought that these shock absorbers could not be included because, in this case, since the members of the design are composed of spaghetti, like placing members like joints in the middle of a spaghetti member will basically will easily break the spaghetti because spaghetti breaks like easily in the middle. You can support like in the joints, but not like pasting in the middle of the member. And finally, we have the NASA Viking 1, which is the first U.S. mission to land a spacecraft safely on the surface of Mars and return images of the surface in 1976. Um, and the structural design is composed of is the same as almost the same as the InSight mission. It's composed of three more legs, each with two supportive shock absorbers, like here. And we also see this pattern like design, well, not pattern, like design idea, like the legs here, and then the supported shock absorbers are like a little below the level of the leg itself. And this inspiration actually took like major consequences for choosing the final design of the lander. So this is basically the first sketch for the lander. This is like a side view and then a 3D view. I I thought that maybe that the better way to protect the eggs will be to kind of enclose it in a jail, like a personal jail. I mean, the egg is like that. This jail was created for the egg itself. I mean, you cannot take the egg out of the jail. And out on that, it's composed of this this is square frame here, square frame, and it has four legs. Um and then it's like it's connected to the jail is connected to a mainframe with these members here. Sketch number two is basically similar to the inside mission. It's like a circle, and then it has three legs and the main leg and the supportive legs. And this time the jail for the egg is a triangular, like a prisma, and it's like a little above the circle. However, this was like disregarded like immediately after it started working, because it will be very hard to actually mold the spaghetti into a circular way. It could be done, but it's very hard and not necessary. And finally, the sketch number three is the final sketch that I choose for the design, and very good results were obtained with this sketch, because it is kind of similar to sketch number one, but instead of having two frames, it has two frames here, like this one and this one, like square frames. They're connected by these small members, allowing to be like placed one above each other. And then the jails place it like in the middle of the egg, and it's connected by members like here and here, like more members than in sketch one. And also the legs are two legs like one above each other, giving the design some stability and very nice force constellations concept that I I'll explain in a moment. So this is what I was talking about. So for example, imagine like the normal force of impact like basically acts vertical, no? And then so for counteract this vertical force, the leg in the lander will have to create a vertical force like, well, like downwards. So a force in the member will be created, and because of that, like by having the y component exactly equal and opposite to the normal force here. So and by doing that, this member will be in compression. So when place it, the force here will basically be decomposed in one vertical component in the y direction, in the z direction, sorry, and then another components in the x plane and y plane. So, for example, this vertical component will be like this way. Mhm. So the member will be in compression, and the member would act itself to counteract this force with this force like in black arrows here. So, but okay, you can take it like so. Okay, so this pushes the member like this. The member needs a compression. But however, there is also another leg here, and the member here also provides a compression force that is in the same way decomposed in the y and in the xy plane. So the impact force creates a force that goes like this, and then the member is compressed and it creates another force. So this pushes the member, tries to push the member in that way. Okay, but what if now is that we actually have another member, another leg here that is pushing the same member like this. So if the impact is kind of symmetrical, the force will distribute and cancel here in the four members of the design. So it will basically allow a very nice force cancellation. And the same applies to sketch number three, but better, but even better, because you have, instead of having two members, like one frame, you have two. Yeah, sorry. You have one two members like placed one above each other, and each of these frames have its own leg. So this creates a force like this and this. But there's also this leg that creates the force like this and like this. So all the forces here ended up canceling. So I mean, I didn't come out with this because this was inspired by reviewing the NASA designs, how they place it like some legs like above below others, but it led to pretty good results. These force cancellation concepts. So this is the final design. Here is the jail egg, and the two frames, the legs, place it along the shore, like reinforce it. This is side view. These are the dimensions. The upper leg is 9 centimeters. The below leg is 6 centimeters. 12.5 centimeters here, and from like the sides of the frames, and the height of the jail of the egg is 7 centimeters, and the part of the square above the egg is 5 centimeters and 3 centimeters, and finally we have 6 centimeters for this member here. This goes from the structural base to the top of the jail, and 4 centimeters for this member that goes like this, uh, that is like a support for the second member, for the second frame, square frame. So the lander was placed in the landing pad. This is a 30 centimeters roll, so it fulfills the requirement. Um, the velocity. Okay, so for the velocity calculations, just apply some kinematic equations, and we got I got 4.43 meters per second, which is equal to 15.95 kilometers per hour. And okay, for the normal force, basically to determine the normal force transmitted to an object moving at a certain velocity in a collision, you need to either have the distance the object travels before stopping, or the time it takes to stop the object to stop. Okay, so since it's really hard to like it's really hard to determine the actual distance, like collision distance, because you cannot determine it with the soil. You will have to determine the deformation of the deformation of the soil, so it's like impossible to determine that. You have to. So since we cannot get the collision distance, the time interval was estimated using the slow motion video recording capabilities of a cell phone, an iPhone in this case. And okay, so how did you do that? Did I do that? According to iOS, the slow motion videos are recording 240 frames per second, and by watching the video frame by frame, it was determined that the whole collision of a 1 meter drop took place in 10 frames. This led to the following calculations. So by just doing the conversion, 240 frames per second, we get that the collision took place in 0.042 seconds. By placing that, we get the value for acceleration and the value for force, using this method I will show in a moment. And the analytical calculation after doing the method of joints here in this joint, after applying it, we get these equations, and we get the force in member AC to be 22.463 newtons in compression, and the force in AB in 15.246 newtons in tension. And the weight of the lander, it was estimated to be just about 400 grams, and because look, so I weighted the lander without these two supports here, like two top support for the jail of the egg, and then it weighted 0.3 kilograms, and then just after place them, it weighed 0.4. So it was estimated that this scale is rounded like completely off, rounding off, and not rounding at all. And the weight of the lander was estimated to be about 400 grams. Okay, so these are the videos for the performance. This is 1 meter drop. So the egg is fine. Then 1.5 meter drop.
Okay, so this is the second test. It's like the height of the. Well, actually, this is like this, like meter and a half. Yeah.
So the egg still didn't break.
Okay, so this is the second test.
And finally, the final test I did was from 2.3 meters.
Okay, so this is the fourth test. Is it like higher? The roof is a little higher in my house. It's 230 meters. Let's see. Okay. Yeah, so the model is like half broken, but the egg is perfectly fine here.
So pretty good results were achieved. Uh, this is the maximum drop distance I couldn't afford for the egg. So uh, for the final performance, I registered 5.75 meters per kilogram. Okay, conclusions. The lander build met the design requirements with a weight of approximately 400 grams and a size less than the 3 centimeters times 30 centimeters landing pad. The lander met and exceeded the performance requirements, being able to withstand a drop from 2.3 meters without breaking the egg. The impact force transmitted to the lander was calculated by estimating the collision time of the lander with the floor. Using the impact force, the forces transmitted to one leg were calculated by using the method of joints and determining the force, tension, or compression in each of the members is subjected to. Okay, for further improvements in the design, I will reinforce more the legs, avoid the breaking of the legs, because of use on the 2.3 meters were the legs that the part that was breaking, not like the structure itself with the jail of the egg. So it will help to have more reinforced legs. These are the references for the NASA designs, and thank you for your attention.